Kevin, as you know, many of you know, is a research associate professor in the Civil and Environmental Engineering Department at Vanderbilt. Between '86 and 2002, at the Savannah River Lab, he was recognized as a DOE complex-wide authority in process and product control for high-level waste vitrification. He spent 2002 and 2003 at the International Institute for Applied System Analysis in Luxembourg, Austria, where he, I pronounce it wrong, it's Luxembourg, Austria, where he estimated potential transboundary radiation doses resulting from hypothetical accidents at Russian Pacific Fleet sites. His current research is supported by the multi-university consortium for risk evaluation with stakeholder evaluation, risk evaluation with stakeholder engagement, CRESP. His current research focuses on life cycle risk assessment or risk evaluation, model integration, and waste management issues related to processed advanced nuclear fuel cycles, and in particular cementitious materials and barriers for nuclear applications.
Thank you. So Bruce, that was a fun deposition study because we covered about 1/10 of the surface of the world. So that was a fun one. So I worked with a meteorologist, a Russian guy, so that was a fun study. So Kevin Brown, this is a program update, so it's going to be fairly broad but fairly shallow in terms of the scope. I'll field questions later because I'm going after this, so any questions you want, let's hit it now. So I said this is the CRESP group, and so this is all the work that we're doing to support PAs, or at least touching on most of the work that we're doing. This involves Vanderbilt, and it involves a number of people out of the Netherlands, and so work that's been going on for several decades at this point, if you consider the leaching stuff that David talked about yesterday. So we kind of framed this idea of how do we generate a set of tools to support PAs and other related questions for long-term performance of cementitious waste forms and barriers, looking at aging, degradation, and leaching. So it's how can you improve the assumptions underlying the performance of disposal vault concretes at, say, at Savannah River. We've got an active program with Kent Rosenberger where we're looking at these things. How do you look at the long-term performance of a similar material, cast stone, at the Hanford site? How can you test for and look at the underlying assumptions for PAs associated with waste forms just in general for near surface disposal? And how can you make those release estimates more accurate? And then we've also taken a look at how you look at the closed waste tank and the performance of that over time under different scenarios. So we kind of tried to frame it that way. We've had a number of applications we've looked at over the years. Hanford site, single shell tank waste integrity, Waste Management Area C, which was the first one they pretty much have retrieved the waste from, still working on one tank. And then the next one is AAX, so we're looking at that. And again, that will be more of a PA maintenance sort of idea, that and the IDF, which is under review, its performance assessment. Looking at how do you look at the source term and characterize the source term for cast stone, selected for secondary waste at Hanford, also looking at it for low activity waste and non-high level waste. With the reinterpretation, you'll see the phrase non-high level waste, and that's kind of related to the reinterpretation of high level waste and however that goes forward. In situ grouting, dry storage of cesium and strontium capsules, we're looking at that in terms of gamma effects. The Savannah River, I mentioned the ongoing program we have with Kent Rosenberger looking at salt stone, so high salt waste in contact with the vault. How do you look at that as a PA maintenance, a special analysis sort of idea? And then at Oak Ridge, we're looking at treatment and disposal. They have a lot of mercury at Oak Ridge. And then how do you look at something like Y12, where you have a building that size? How do you look at debris, disposition of debris in a place like that? If it's above a certain, BDAT is you reflux it if it's above a certain concentration. Refluxing Y12 is a bit daunting, so what are you going to do instead? Because that probably isn't going to happen, but who knows? So we're looking at that as well. And then, as I said, for the dry cast storage, we're looking at the performance of those, especially the gamma effects on the dry cast storage, and also looking at the Hanford site, maybe related to the cesium and strontium capsules. So major activities, they range from the experimental to the modeling. I tend to do more of the modeling stuff. David and others do more of the experimental. We are looking at evaluating the impacts of oxidation and carbonation on these waste forms, the cementitious waste forms, and how they perform over time. Looking at the leaching chemistry, density, saturation. If you got something like a high salt waste, typically the way you would measure porosity on something like that you can't really do because you add water to a high salt waste. Guess what? The salts dissolve and you can't really do porosity that way. So you have to look at doing that differently. We've done a lot of work on that. David had mentioned the work for applying the leaf methods to low activity waste glass. I won't touch on that today because he did a good job with that yesterday. And then, as I mentioned, for things like dry cast storage, what's the effect of long-term high gamma radiation on those sorts of materials? So on the modeling side, which is what I do more of, we're looking at how do we close the software quality assurance that came up yesterday. On the methods that we use, our methods kind of grew out more of a research environment. When we apply these things to DOE work, we have to be consistent with 414-1D and NQA1. So we're working towards that. As David mentioned, we've got the pH dependence models. That's the 1313, the 1315. These models are already in SW 846, so they're being used actively for regulatory purposes. But how do we make sure that our software quality assurance is consistent with DOE regulations? We've looked at a number of these models. We've just started the work on the column models just this quarter. So that's all progressing very well. Then also, as we talked about, there's things like high salt waste at Savannah River in contact with a vault concrete. People have done experiments where several years they put these things in contact. You're supposed to have sulfate attack. You don't see it. So we're looking more at that interface and the effects of the conditions on whether you actually get sulfate attack or not in the time frames that we care about. So we're looking at that as well. And that's, like I said, an ongoing program with Kent. So we have a series of models that we use to describe the same test methods that David talked about yesterday, 1313, which is pH dependence, 1315, which is mass transport. So you can change your field conditions, your laboratory setting, different materials. We've looked at several thousand materials in this database that we have called LeachXS. You can also, there's an integrated geochemical model called Orchestra that I'll talk more about that you can use to predict the same things you're seeing experimentally. Change the interface conditions, the flow conditions. We've done some work under what used to be called Cementitious Barriers Partnership where we transferred these models to GoldSim. Our students tend to use MATLAB more just because they're more familiar with it, but we've done both MATLAB to use as a wrapper around these things for probabilistic work as well as GoldSim. So in terms of the SQA, this is painful because this is what I've been doing the last 2 years. We're making our models and our test case and our SQA consistent with NQA1 and 4141D, which is the DOE quality assurance order. So we've kind of progressed from very simple calculations with analytical solutions all the way to, say, code-to-code verifications or checks with things like FreakC. There's a number of international benchmarking studies that our codes have been compared to. This one, the reactive transport, this one here, is one that in the Netherlands are looking at boom clay to dispose of the radioactive waste. And that's the same calculation that we're using as one of our benchmarking studies and one of our test cases. We've also compared things to laboratory and field results because we also talked to the NRC and they're like, well, what does this mean in reality? So we've tried to do a lot of work. I did a case back a few years back looking at the C107 dome core from the Hanford. So it's buried 65 years under 3 meters of dirt. They took a dome core. So I was able to predict, not calibrate, but predict the level of carbonation in that dome, and it was very consistent with what they actually saw experimentally, so that was nice. We've done a lot of work looking at the monolith models and how these work, and we're still developing the comparisons there. Like I said, we're just starting the column models now, and then we've looked at sulfate attack, and I know the sulfate attack model, which is used for Savannah River and their saltstone. There were a number of questions that the NRC raised on that, and so we're still working through some of those in terms of how the model is formulated and how you handle that, some of those things stochastically. So that's an ongoing project as well. And I'll talk more about that later in terms of the work that we're doing with Kent. So David touched on these already. So there are 4 basic methods in SW 846, leaf methods, EPA methods. You've got a 1313, which is a pH dependence model, so release is a function of pH. You have 1316, which is release as a function of liquid to solid ratio. You have mass transport rate tests. David talked about the 1315 test. And then you also have some percolation column leaching tests, which we're just engaged with doing the software quality assurance for those models now, where it's an upflow column looking at the liquid equilibrium and the liquid to solid ratio. So again, pointing out that these things mean something in the real world. A great deal of work has been done relating the leaf methods to actual field results. And there's an EPA report that David and others had worked on to look at the leaf methods for a number of different materials. And of course, this is 7 out of the several thousand that they've looked at these leach methods for. So this is obviously available, and also recommended how you use leaf to address some of these field conditions. So this is a very useful report. So I'm going to get into some of the experimental work and some of the motivation of this. So we've looked at a lot of effects of carbonation and oxidation on both vault concretes and high salt waste materials. This is because, these sorts of things can affect not only the microstructure of the material, but the redox state and therefore some of the solubilities of key constituents. So we've been looking at that. And then the effect of, when I was looking at the tank closure scenario for a 65-year-old Hanford tank, I didn't really have to worry much about supplemental cementitious materials. But when you look at, say, vault concretes at Savannah River or IDF at Hanford, you're going to have to start worrying about supplemental materials. So what are the impacts of these on the alkalinity and some of the other effects that you're going to see? So carbonation is recognized as one of the primary degradation or / aging mechanisms for empty tanks at, say, Hanford. So it's important from that respect. So there are a number of reactions that can happen as you get CO2 from the soil gas or from the atmosphere in contact with the concrete. It can lead to changes in pH, which if you have a significant change in pH, say to pH 9, you can get depassivation of embedded rebar. That can lead to expansion, maybe even cracking. So it's something that could change the structural properties as well, the advective property, the flow properties of the material. It'll change the solubility of certain key constituents that you care about. Like I said, the microstructure can change. And then there have been just limited studies on the impact of carbonation in these waste forms for small amounts of Portland cement, which is where people go. But these changes depend on the material. So if you have something that is, say, Portlandite primarily, and you start carbonating it, you'll get a refinement of the pore structure. But if you have something like a geopolymer or something with ettringite in it, as you carbonate, you actually lead to expanding the pore structure. So it does depend on the material. It doesn't always close the pore structure. Sometimes it can open it up. So you have to be careful what kind of material you're looking at. In terms of the oxidation, everybody in the room is familiar with what happens to technetium under these conditions. I'm not going to get into that very much. But we, in our work, because we try to limit the amount of rad material in our lab, we looked at putting chromium in as just kind of a redox sensitive species so we could kind of see how the fronts move. I'll talk more about this later. So again, in terms of supplemental cementitious materials, often things like fly ash or blast furnace slag is added to change the properties of the material. Say if you want to increase the redox capacity of the material, you might add slag to affect things like keeping their technetium in the material. So this is important in terms of, the addition of this can be important in terms of how the oxidation and carbonation affect the material. So we did a couple of experiments. I'm going to just talk about, I actually did a lot of experiments. I'm going to talk about a couple of them. So the first one is looking at the vault itself. So what we did was, if you're looking at things like SEM, you really don't want to have the aggregate in there, the large aggregate, because it makes it hard to interpret anything on SEM. So what we did was develop a series of, and I should say Janelle Branch, a former PhD student, developed a series of what we call microconcretes. I think we've actually called those sieve concretes now, where the idea is you take the surface area you would get from the small aggregate and the large aggregate, and you conserve that surface area, and you'll see the leaching properties work about the same as if you still had the large aggregate in. So it's a good surrogate for a vault material if you're going to do things like small-scale SEM and other analyses, which is what we're doing. So this is basically looking at how fly ash replacement, 45% of the Portlandite being replaced by fly ash of various alkalinities would affect the carbonation, the oxidation of the material. You see these things were all aged initially for 6 months, and then carbonated or oxidized or put in a oxygen environment. So we did carbonation only, oxidation only, and carbonation oxidation combined as this series of studies, and I'm just touching on a little of them, but this is all in her dissertation. We also looked at the alkalinity of the fly ash itself. So as you can see, there are some significant effects. If you carbonate the material, you'll see the CSH in the Portlandite will deplete, and the vaterite and the calcite, and vaterite is an analog for calcite, will increase, which makes sense because you're carbonating material. So this is what you expect to see in something like a concrete, and this is thermogravimetric analysis. So you can see some pretty profound effects from the carbonation. You can also see, because people often talk about pore structure refinement when you carbonate something like a concrete, you can actually see that as well. These are small scale scans of the material that will show that you do get some definite changes. So the one on the left is the uncarbonated, and then it shows to the right of each the effect of carbonation. And you can see also the alkalinity of the fly ash you've added. So let me explain. The 00 is the one without any fly ash addition, so that's just Portland cement. And then you have the 39, which is the moderate alkalinity one, and then the low calcium fly ash is the O2. So you see effect of not only the carbonation on the pore structure refinement, but you can also see an effect of how much alkalinity was in the fly ash itself. So it also depends what material you're adding to it as to the response you get. We also looked a lot at the high salt waste form. We've looked at saltstone, but I'm going to talk about cast stone today because this is what is ongoing now. So basically we're looking at the average H2 simulant for the Hanford as the simulant that we're using in these cast stones. And basically we're just going to cure the material for 90 days and then prep it for both carbonation and oxidation, very similar to what we did with the microconcretes, to see what the effect of carbonation and oxidation is on the cast stone materials. So again, age 60 days, looking at doing thermogravimetric, 1313, which is pH dependent test, XRD, total inorganic carbon. We're doing SEM on these. We're doing the monolith testing for mass transport. So we're doing a suite of tests to try to characterize the behavior of these materials and the effects of carbonation and oxidation. We also looked at the relative or the saturation effects on these materials. So this is the second series of tests where first we're looking at carbonation and oxidation, and we're also seeing how the saturation for these materials, because these high salt wastes really want to soak up water, but as you start reacting things, they also produce water, so you have to kind of keep track of the water in these materials. A place like Savannah River, it's pretty much saturated. A place like at Hanford, it's not saturated, so they're very different environments. So we're kind of extending what we did for saltstone to the cast stone materials as well. So the next two plots, I may have accused the student of making these data up because they just looked, the variability is so small, the uncertainty is so small, it was hard to believe. This one is looking at the effect of relative humidity based upon the carbonation effect. You can see you have a fairly linear, with square root of time, effect of carbonation on the depth, of relative humidity on the depth of carbonation. You'll see the literature would say that it should be proportional to the square root of time, and it looks pretty proportional. Now, I had a statistician who would have said a line is a point in an opinion, and so those are still pretty good. So we see a very strong effect that agrees with kind of the literature that would say that it should be proportional to the square root of time. So. And then also looking at the effect of how much carbon dioxide you have in the test chamber that you're curing it with on the rate of carbonation, And you can see this apparent linear. This is one I actually said she probably made up because this one is, I guess this means she didn't make it up, but the rest of the other ones fall right on the line. Those data are almost hard to believe. So you see this apparent linear relationship between the carbon dioxide level and the rate of carbonation. So other effects, and again, this is on the cast stone material. You can see some effects based upon whether you're carbonating, oxidizing on both the pH-dependent test and the mass transfer test. You can see the change from carbonation will affect the solubility at the natural pH, and that is, in the leaching world, that is where you don't add any acid or base to control the pH level. You just kind of let it go where it wants to in terms of the leaching itself. You can see it affect the initial mass transfer releases because of this effect on the natural pH. And you'll see this shift at, say, 63 days over here. And we attribute that to the fact that the leaching front relative to the carbonation depth have kind of crossed. So you kind of see that effect in these. For oxidation-sensitive species, and again, this is chromium and iron, you'll see, again, an effect on the natural pH. Again, affects the initial mass transfer release. And then you'll see after 21 days for this, you'll see this shift in the mass transfer. And that's, again, relative position of the oxidation front to the leaching. And then the shift that you'll see in the mass transfer in the early releases is, we suggest, is the fact that the oxidation front is moving more slowly than the carbonation front in these materials. So the fronts don't move. Even though you would think that the oxygen and the carbon dioxide are kind of moving into the material because it's unsaturated, at the same rate, you'll see the effects actually going through the material at different rates, so the fronts move differently. I only have one slide on this. We've been doing a lot of work with Kent over the year to support the revision to the SDF, the Saltstone Disposal Facility, PA, at Savannah River. So originally they have an assumption that you have a vault and you have CO2 from the soil gas on the outside of the vault carbonating the material, and you have salt waste on the inside, sulfate attacking the material, and at some point those fronts will cross, and they say material then, I shouldn't say magically, then becomes just like the backfill soil in terms of the hydraulic conductivity. So it's a fairly bounding assumption. I won't say conservative because David Esch is here, but I'll say a bounding assumption. And so how do you look at the hydraulic conductivity of the intact versus the degraded material? There was an initial assumption that, there are kind of two bounding cases. You either assume flow kind of parallel to it or parallel to it or perpendicular to it or parallel to it. If you go in the literature, and Craig Benson at Virginia helped me out to look at this, if you do a weighted geometric mean of the two based upon the uncertainty in your hydraulic conductivities, you get a much better representation of the intact versus degraded than you do by looking at either of those kind of bounding conditions. So this is something that I at least hope, at least I've been told it's going to go into the PA. We're also, like I said, looking at the interfaces. There was a former series of tests done at Simcoe Technologies where they actually put saltstone in contact with vault concrete for, I think, at least 2 years. And they looked at it even on SEM, and they could not find any sulfate attack. So we're doing a series of tests looking at this as well. Andy Garabrandt at Vanderbilt is heading this one, where we're doing a similar study looking at, do you actually, not only do you see the sulfate attack, but what are the reasons if you're not seeing it? Because that would be very important to PAs in the future, at least salt in high salt waste in contact with vaults. The last thing I want to talk about, this is kind of new to this group. I know some of you have heard the other stuff I've talked about. In terms of dry cask storage for things like, we're all hopefully most people are familiar with the TMI2 dry casts at Idaho. They had some issues with those. So we're looking at how do you improve the performance of the cementitious materials you might put in things like dry cask storage. One of the effects you might see is the high gamma, depending on what you put in these, coming off the waste itself. So what's the effect of that high gamma on concrete? We have a tremendous amount of information on what neutrons do because, reactor vessels have lots of concrete in them and they get hit with lots of neutrons, so you know what that does. But how do you look at the gamma effect? So we took some material, went out to Oak Ridge for the high flux isotope reactor and hit it with gamma, representing, say, up to 100-year of impact on the concrete itself to see what the effects might be, both also as a function of temperature. So we have these data, and we're in the process of analyzing these. This is Professor Florence Sanchez at Vanderbilt who's working through this. And so we're doing a bunch of series of tests on these and looking at how the gamma might affect the concrete and how to improve, say, the performance. This work is geared at putting nanomaterials into concretes to help improve their performance, and this is how one of the ways we're looking to see what the effect of that would be. So I am done.
Right
Any
on time.
questions?
Thank you. Question for Kevin?
Please.
Thanks, Kevin. I have one question, one comment. So a question first. Did you, maybe I didn't get it or maybe you aren't there yet, did you see any synergisms or throttling associated with combining two processes, i.e. the carbonation and the oxidation at the same time in terms of the waste release?
You don't see too much of that, but one of the things that came up is just what you're talking about, because I know you and I have had these discussions in the past, as I've had with students, that first it was just going to be oxidation and carbonation. I'm like, well, that doesn't, we have to have both in there as well, which, you know, the researcher doesn't like because it's more work, but
right.
How do you isolate these and look at the synergies? We haven't seen too much of that, but it's an ongoing process. Okay. Because with the microconcretes, things happen less quickly. So I think on the vault side, you're not going to see too much. Things like a 60% porosity cast stone or salt stone, you see a little more of it. Right. But again, then you're much more worried about the oxidation effect than you are on the carbonation effect, because you're not going to see a whole lot of carbonation on those. Right. But we kind of did it so we could understand the basic mechanisms of that. But it's a good question.
And then my comment is I'm very encouraged to see this, because if there's one area of the performance assessments where I think you can get a lot more performance out of it, or maybe in rare cases lesser performance, it's in the area of the waste form and the material science. Everything that's right. going on inside of that area of the problems is probably understudied or underutilized is the way I would describe it. So.
Well, and the whole thing about uncertainty, because I've done a lot of going back to the high-level waste program at Savannah River, you know, people talk about uncertainty, but typically when you start characterizing uncertainty, it gets bigger first, which people don't like to talk about, but it tends to get bigger, and then it gets smaller. And I know Roger's nodding back there, but that's typically the nature of the beast. When you start looking for things, you find them, and then you have to start addressing them. Sorry. Anything else?
Any other questions? All right.
Thank you.
We got an easy time this time. Thank you.